Welcome back. In episode 5, we will look at the 10-twist tumble torus. In the last episode, we saw how a series of twists made a tower when it was tightened up, but when it was loose, the tower was able to dangle freely. The top of the tower is actually free to move anywhere on a kind of hemisphere shape, but it stops bending lower because of the tightening of all the twists. Under the influence of gravity, the top of the tower traces a horizontal circle where the twists just get tight enough to prevent further bending. It makes you wonder how it would behave if the top of the tower was bent around and connected to the bottom of the tower, making a kind of donut shape. Then it wouldn't need gravity anymore at all, and it would stay curved at the maximum all the way around. For that, we're going to need 10 twists because the curve is just a bit too tight for 6 or 8. Remember last time I packed up the 6-twist tower into a box? Keep in mind, all you have to do is order 3 vertebrae from getpretenst.com and I'll send one of these to you so you can have your very own. Well, it just so happens that I still have the 6-twist tower packed into a box, so to make the 10-twist tower, we start with 6. I just have to disconnect the ends of the tower and extend the tension network all the way around the circle. We're going to need to add 4 new tension hexagons, so that's what I'll make first. 4 hexagons is 4 times 6, so I'll need 24 cables of the shorter length. A while ago, I made this simple jig to speed up the preparation of cords. It's made of 2 aluminum plates with slits, held at the right distance from each other by some threaded rod and a few nuts. First, I cut the 24 lengths, leaving a little extra length at either end, and then I melt the ends of the cords with a blowtorch to create blobs. Then it's quite easy to make simple knots and connect the cords to each other via the metal rings. So now we have the hexagons, and to attach these and start extending the structure, we tie the 3 loose ends of the long cables to every other middle ring of the first hexagon. Now we're going to need more of the longer cords that hold the twists together, but fortunately we only need 12 of these. Same process, but with a different distance between the plates. Cut with a little extra length and then blowtorch the ends so they terminate in a blob. With the longer cords making the connections between the hexagons we just made, we can extend the tension network from the 6-twist tower to build 10 twists. At each new hexagon, we attach every other metal ring. Now, we loosen up the other end of the tower and bring the 2 loose ends of the network together. The tricky part here is to figure out exactly how to connect the cords when the ends meet, because it's nearly impossible to keep track of how it might be twisted. We're going to be needing 4 new twists, so that means 12 new struts. We have to resort to inserting the struts loosely at first so that the tensegrity takes enough shape that it becomes clearer where to make the attachments. As we're inserting the struts, we make sure the twists are alternating between left and right-handed chirality. It's always so rewarding to insert the struts and feel the tensegrity start to take 3-dimensional shape. Now that we can bring the ends together in 3D, we can finally see exactly which connections have to be made. After a little puzzling, we complete the ring and then insert the final struts. Everything is still quite loose, and we haven't yet been careful to make sure all the struts are exactly the same length. We have to go around the whole torus, turning various nuts to make all the struts extend more or less equally. When it's tight everywhere, you can kind of roll it like a tire down the hallway, which is kind of interesting because it means the torus is almost rigid. But with a few turns of the nuts everywhere to shorten the struts, the tensegrity becomes loose enough that you can see a really interesting different behavior. The torus tumbles into itself, kind of like a smoke ring or one of those bubble rings that a dolphin can make underwater. They call this rotation on the secondary axis of the torus, and you can see how this is kind of natural to the loose tensegrity ring. I thought this was such a cool behavior that I got together with my friend Ata from the University of Delft to build a smaller version and motorize the secondary axis rotation. It's strangely hypnotizing to look into the tensegrity ring as it's rotating in on itself. I have to admit, I stared at this for quite a while until I kind of zoned out. We would love to build a much bigger version of this sometime. But that's enough exploration of minimal tensegrity. In the next episode, we will look at how we can add redundant tension cables to make the tower rigid so it doesn't want to bend at all. I hope you can join me.